So let's move on to an exercise now in section 1.8, exercise 1. Let T be a linear transformation from R3 to R3 defined by T of x equals A times x, where A is this 3 by 3 matrix. So since A is 3 by 3, both the domain and codomain are R3 for the linear transformation. What we're going to see is that this language of linear transformation is maybe new, but the calculations here are things we're already familiar with, so we're just sort of describing them in a new way. So let's go ahead and do part A. First of all, we want to find T of u if u is equal to this vector 3, negative 2, 4. Let's just go ahead and do that. T of u is going to equal A times u. And the matrix A is 1, 0, negative 1, 0, 2, 1, negative 1, 1, 3. And we're multiplying times the vector u, 3, negative 2, 4. And so the way we do this now is we take the first entry of u times the first column of A, 1, 0, negative 1, plus the second entry of u times the second column of A, 0, 2, 1, plus the third entry of u times the third column. And what we're going to get is a single column vector. Maybe I'll write 3 plus 0 minus 4. I get 0 minus 4 plus 4. I get negative 3 minus 2 plus 12. So that's negative 1, 0, and 7 is T of u, just that column vector. Okay, so not a big deal. Part A. In part B of this problem, we want to find a vector x such that T of x equals b, where b is given 2, negative 2, negative 3. So we're trying to find an input vector, a domain vector x, that will have the image 2, negative 2, negative 3, right? So let's write what we want to do. Find x so that T of x equals b. And so T of x is going to be A times x. Notice that we're just solving a matrix equation, AX equals b. Again, same matrix A, 1, 0, negative 1, 0, 2, 1, negative 1, 1, 3, times x equals the vector b, was b, 2, negative 2, negative 3. And here, maybe I could have written that. I'll just write this off to the side. So x is a 3-component vector, right? A vector in R3. And so we want to solve this matrix equation. So I'm going to set up my augmented matrix, right? And of course you could have went right to this step if you saw where this was going. So there are the columns of A, and then my B vector, 2, negative 2, negative 3. And then what I got to do is I got to apply row operations to reduce this matrix to echelon form. And I'm not going to write out the steps. So a few steps. I'm just going to go ahead and show us what the reduced form is. I get 1, 0, 0, 2, 0, 1, 0, negative 1, and 0, 0, 1, 0. And so I can read off my solution here. I have x1 equals 2, x2 equals negative 1, x3 equals 0. So our possible x here, or the only possible x, right? 2, negative 1, 0 is the vector we're looking for. So there's an x such that t of x is equal to the vector b. Now, we have no free variables in this solution, right? Because we ended up with 3 pivot positions, so we had 3 pivot columns, one for each of the 3 variables involved in this problem. So this is actually a unique solution. So we can go ahead and answer. I think I can fit it right at the bottom of this sheet. So the answer to C is yes. The x that we have found is unique. There's only one solution to that matrix equation that we set up. And so we've finished exercise number 1, which is on page 4 of our notes. So let's go on to the next exercise. Exercise 5 is kind of similar. Exercise 2, I'm sorry, on page 5, exercise 2. So it's, again, very similar. Here we're looking at a linear transformation from R2 to R2 defined by a 2 by 2 matrix. And in part A, we want to find a vector x such that t of x equals b, where b is given, 6, 0. So now t of x, again, is just ax equals b. So we're going to solve this matrix equation, ax equals b. And let's see, my a is 2, 0, 0, 0. Here my x vector has 2 components, because both our domain and codomain are R2 for this transformation. And the b vector is 6, 6, 0, that's given. So augmented matrix, again, I'm going to set up 2, 0, 0, 0, 6, 0. And I'm going to apply row operations. And notice, I think, if I just divide the first row by 2, I get 1, 0, 3, 0, 0, 0. I think it's already in reduced form. So I get x1 equals 3. x2 is free. And because my second row is just a 0 equals 0 equation, right? I have only one pivot position. And so my solution x can be written as, well, x1 has to be equal to 3. x2 can be anything, okay? And so here, by the way, if we wrote this in its general form, we would have to write this as 3 plus 0x2 over 0 plus 1x2. So I could write this as a constant vector 3, 0 plus x2 times the vector 0, 1. So you want to know how to do that, where x2 is any real number. Okay. And so now I got to answer these parts of this problem, part A. For part A, I can just choose a value of x2, say x2 equals 0, then I get x equals 3, 0 all by itself. Satisfies t of x equals b. So that's the answer to A. There are infinitely many possible ways you could answer that. You could use any value of x2 to get one particular solution. X is not unique. There are infinitely many solutions. And then part C is different now, okay? We're changing the b vector to a different vector. We want to solve t of x equals c, where c is 2, 1. So I'm just changing the b vector to c. I'm going to go right to the augmented matrix. The augmented matrix would be our original A, 2, 0, 0, 0, 2, 1, then goes in the column on the right. And we apply our row operations. And there's only one step here. I get 1, 0, 1. I'm just going to divide the first row by 2. 0, 0. Actually, I didn't even have to do that, did I? Because I can see right off the bat from my last row that this system is inconsistent. I have a 0 equals 1 equation, so the system is inconsistent. And so the answer to C is there. We can find no x. We can find no x that is a solution here. As far as this linear transformation T is concerned, we would say, B is in the range of the linear transformation, but C is a vector, using some of this new terminology now. C is a vector in the codomain that is not in the range. C is not the image of any x vector from the domain under this linear transformation. So we're going to stop this video here and continue in another segment.